All right, so today we're going to cover the chain rule, which is section 14.5 in our textbook. So if you remember back in Calc 1, we had a one-dimensional chain. We had the chain rule in one dimension there. And the way it worked is if we had a function f of x, and x was actually a function of t, then it really is that y is equal to an f of g of t, which to take its derivative, we would take the derivative of the outside piece and multiply by the derivative of the inside. This is typically what we used in order to write it down. But in fact, if you look though, this guy right here is x, this guy right here is x prime. So this is your dx dt term, and this right here is how f is the derivative of f with respect to x. Well, f is y, and so this is your dy dx term, t there, okay? Which is exactly what this formula is trying to say. So dy dt is equal to dy dx times dx dt, which is pretty easy to remember because it looks like the dx's are going to cancel. What's nice about writing it this way is that it's easy to see how to generalize this to multiple dimensions. So in this case, what we have is that z is a function of both x and y, but that both x and y depend on some independent variable t. In this case, to find this tells us then if we plug both of these in here, that f is a function, that z is a function of t. So we can figure out what the derivative of z with respect to t is by doing two separate chain rule parts and adding them together. First, we take the partial derivative of z with respect to x and multiply by the derivative of x with respect to t. This tells us what part is depending on x's dependence on t. In the next part, we do the partial derivative of y and multiply by the derivative of y on t. This is the y contribution to that part there. So as a result, you can see that it's not that much more complicated than what the regular chain rule should be. So let's take a look at how we would do an example. Okay, so let's start out with a function of both x and y, and where x and y are both functions of t, and compute dz dt when t is equal to 0. According to the formula, this is how dz dt should look, and so we can compute each piece. First off, we compute dz dx, which you can just take a second and show that that's the same as this here. Okay, remember we're taking the derivative with respect to x here, and so y would be considered a constant in that situation. Then we multiply by the derivative of x with respect to t, which itself uses a chain rule too. Next, we add that to the partial derivative of z with respect to y, which is the derivative where x is constant, and multiply by the derivative of y with respect to t, yielding this equation here. Now, if we wanted to write everything in t, we could at this point by plugging in all the x and y's for t. But all we want to do is actually find out this value when t is equal to 0. So we can kind of avoid that step. Instead, what we'll point out is that when t is equal to 0, we actually know what x is equal to and y is equal to. If t is 0, then the sine of 0 is also 0, and if t is equal to 0, the cosine of 0 is 1. We can now plug in t equals 0, x equals 0, and y equals 1 into this equation here to get the value of dz dt when t is equal to 0. And this is what we get. You plug everything in, and you simplify, and you get 6. The next case is what happens if z is a function of x and y, but x and y themselves are actually also multivariate functions, so they both depend on s and t. Well, in this case, if you were to plug these in, what you'd find is that z is actually now a function of s and t. So there isn't a total derivative anymore for z. There's these two partial derivatives. There's partial z partial x, and partial z partial s, and partial z partial t. And the chain rule formulas for those follow much the same way as the regular derivative formula did too. If we take the partial derivative of z with respect to s, we do the partial with respect to x first, and then what x's dependence is on s. Then we take z's dependence on y and multiply that by y's dependence on z. and a similar thing for partial z, partial t. So this formula is not too hard to remember because in both cases you notice that the partial z's kind of look like they're canceling and the partial y's kind of look like they're canceling, and those are the two parts that make up the whole. To do an example, let's let z be a function of x and y, where x is a function of s and t and y is a function of s of t, and find both of these partial derivatives. Well, the partial derivative of z with respect to s follows this formula here, and so we can compute each individual piece. We'll take the derivative of z with respect to x and multiply by the derivative of x with respect to s, and then add the same thing with using y. If we do that, we get this line here. Since we're not plugging anything in here in order to get an actual number, it'd be good to write everything in terms of t, and so what I did is I took this x and I plugged in what x is, and the y I plugged in what y is, and then rearranged, and I end up with this is my first term, and this is the second term. It turns out that this is exactly what we would get if we actually plugged these in first. If you plugged these in first and then computed the partial derivative with respect to s, you would have to do a product rule on this piece and two individual chain rules, and that would produce the sum and the individual chain rule pieces that you would need to get, and hence lead to the exact same number, the exact same formula we got before. When we do this with respect to, that should have been with respect to t, no, that's right, with respect to t now. In this case, we notice that partial z, partial t follow this formula, which we can then actually compute. So we do partial z, partial x, multiplied by now partial x, partial t, and so on. And then we plug everything in to get here. I recommend trying to do this problem on your own, just to make sure that it made sense, instead of just seeing it here so that you can see how each of the different pieces are. So this might be a good place to pause and try maybe this example and the first example we showed on your own in order to try to see if you can get the same answers that we got here and see why all those things work. All right, so this leads us to the idea of a chain rule of a general version, which is if u is a function of a bunch of variables, x1 to xn, and each one of those is a function of m variables, t1 to tm, then you can do then u ends up being a function of these guys here, and you can take the partials of each individual piece. At any point, partial u, partial ti, for whatever index you pick, would follow the exact same pattern as before, where you've got all the x1s canceling, looking like they cancel, the x2s looking like they cancel, and all these individual parts adding up to the whole. We won't do an example of that because we've already done a couple of examples of simpler cases. Now let's take a look though, because implicit differentiation is something we actually already know how to do, but using this idea of the chain rule allows us to view it a little bit differently. So suppose y can be written implicitly as a function of x, which we could move everything to one side and think of it as some multivariate function, capital F of xy equals 0. Well, in that case, if we differentiate both sides with respect to x, we have to use a chain rule on this piece, which would give us the partial derivative of f with respect to x times dx dx plus the partial derivative of f with respect to y times dy dx. The dy dx is the piece that we want, and it turns out this dx dx is actually equal to 1. So I end up with just partial f partial x plus partial f partial y times dy dx equals 0. If I want to solve for dy dx, I'd move this guy to the other side of the equation and then divide by that. So that's exactly what I get. Here's dy dx, here's partial f partial x with a negative because I subtracted it, and then I divided by the partial f partial y, which in another kind of shorthand looks like this. So let's give this a shot and see what happens. So here's a standard implicit differentiation problem. You can actually do this with methods from Calc 1, and I recommend doing it with that method now just to see what the answer should be. Then let's try it with the method we just described. First, we're going to move everything to one side of the equation like we said. This ends up becoming our capital F of xy, which is what I wrote here. Now we can follow the formula that dy dx is negative fx over fy, So we take the partial derivative of this with respect to x and put it on top, and the partial derivative with respect to y and put it on the bottom. If you did like I said and did the implicit differentiation via methods in Calc 1, then when you do it this way, you should see that this is actually exactly the same answer. And so that's kind of a quicker way to get to the answer for implicit differentiation. Although it does require you to remember a formula, so it's kind of up to you whether or not you use it this way or not. What's nice about this, though, is that it extends to higher dimensions. So for example, if I have f of x, y, z, I can use that to differentiate with respect to x to find out what partial f partial x is going to be, and hence partial z partial x. So in this case, I've got this guy is an implicit function, so z is implicitly a function of x and y, but I can't solve for it for some reason. Okay, so I need to use the chain rule here to see if I can identify this. So I get partial z partial x, that's the guy I'm looking for. The partial y partial x, because x and y are independent variables, when I take the partial derivative of one independent variable with respect to another one, this is going to go to 0 because y is a constant as far as x is concerned. Over here, this is 1. So when I put all that together, this is the formula I get, and this has to equal 0. Differentiating by y yields a similar equation there. If I solve both of these for partial z partial x and the other one for partial z partial y, I get the following, which yields that partial z partial x looks like this, and partial z partial y looks like this. So if I wanted, whenever I run into implicit differentiation problems of trying to find partial z partial x and partial z partial y, I can use exactly the same method with the chain rule and be able to handle it there too. That's pretty much all there is to the chain rule and multivariate functions. And so I hope that this that these examples were clear enough that you can handle these problems now. What I would recommend is maybe, again, going back and trying each of the examples we did in this video yourself to see if you can get the same answers at this point. Try doing it without watching the video, and then watch the video again, or those parts of the video, to see if you did it right, and see if there are other things you need to fix. If you have any questions, please feel free to email me. Otherwise, I'll see you guys next Wednesday. Monday, of course, we don't have school because it's Martin Luther King Day. But besides that, you guys are good to go. Good luck on the homework. I hope you guys have a good weekend.